Hello class, welcome to this week's lecture on neural networks. We'll be looking into detail on what a neural network is and how does it work before moving into the second lecture for this week, which will be about the different types of neural networks you may encounter. Neural networks for speech, for language, time series, images, etc. First of all, why do we use a neural network? We basically use a neural network when we cannot draw a linear line to separate our two classes. Okay, so in the case of this image on the left here, we have purple dots and red dots, and we can't just draw an image to separate them. Instead, if we use a neural network, this allows us to come up with any polynomial function that might separate these classes. In this case, it might be a circle. So this gives us the flexibility to deal with very different type of data. Neural networks, actually, as you saw in the lab from last week, problems like XOR, very simple problem, right? You have 4 inputs and there's only 1 or 2 possible outputs. Still, we cannot separate it with a linear line. Our logistic regression model did not work for this problem. Okay. So we need a more complex polynomial function. So this week, from the lab or the homework, I forget, we'll see if we can use a neural network to solve this super simple problem. Okay. Now, neural networks are typically depicted or drawn like the figure on the right. What does all this mean? We have different layers in a neural network. That would be the vertical columns. If you have more than one layer other than your input and output layer, so you have your input layer and your output layer, then we call this model a deep neural network. So deep neural networks have many layers in between. Each layer consists of nodes, which are just the little dots in the center. And we'll have a look at how the output value of each node here, everywhere, is calculated simply as a linear combination of all its inputs combined with weights. Okay. So for instance, this x here will consist of a linear combination of all 4 of these inputs. Okay. Right. Oh, we have a nice animation here of how a training barrier evolves during training and can be made nonlinear. Okay, so each set of neurons, so each neuron, which is a ball in the previous figure, each neuron's output is formed as a linear combination of all its input. Okay, then this linear combination is put through an activation function G to form the actual output of the node. Okay. What does this mean? When we calculate the input value of the node, we have a linear combination of all the x's with a vector of all the weights, plus a bias term. Okay, the bias term just shifts the result. Then we'll calculate an activation function of z, z, to calculate the final output y hat, it's predicted y. Okay. Now, interestingly, this whole perceptron model was first invented or intended to be a mechanical hardware. So it wasn't really software. It was built as hardware. It was called the Mark I machine, and it was actually used for image recognition tasks by the US Navy. I have a little video here to show you the very first perceptron built as a hardware. How do we play that?
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Okay, do you notice how they say that this technology has died out? Definitely because of the AI winter. And I can tell you that using image recognition for using neural networks is very much popular today, as you all know. So I've already very briefly showed you how the perceptron works. Let's go over it again. So we see that we have a node. The node is here split into two elements. We have these two are actually the node. We have first a linear combination of all the inputs. Typically also has a bias, but sometimes we omit this for brevity. And an activation function. In the case of logistic regression, in fact, this is basically one perceptron. Okay. Remember, logistic regression first does a linear combination of the inputs, and then it feeds it through a sigmoid function. Okay. Basically, one perceptron. Okay. The activation function is what makes these linear combinations non-linear. Okay, so they would allow your network to learn these complex shapes. I mentioned that usually we add a bias to the model. So here, bias will also have a weight. Okay, it just shifts our model. Now, if we rewrite this a little bit, so using linear algebra, we can actually replace the whole summation over all the different weights and replace it by a vector W. The vector W will be a vector of all the weights. The vector X will be a vector of all the inputs. And we note that we need to transpose X so that we can take the dot product of both. All right, so activation functions. Once we have this linear input, we apply an activation function G to our linear combination. In this case, let's take an example and we look at the sigmoid activation function. So sigmoid takes any real number and transforms it into a scalar output between 0 and 1. So it's a very bounded output, ideal if we're predicting probabilities. I've added a little plot here as well, so you can see the sigmoid function, but we talked about this one in detail in the last class. Okay, but there's a number of other activation functions that we could use. I put a few common ones here, but there's a bunch. I added a link to the PyTorch documentation where you can actually find an enumeration of all possible activation functions. Okay, sigmoid, we talked about this just now. You can easily call this in PyTorch using the command torch sigmoid. We could have a simple threshold function that basically cuts the output of our linear combination of input variables using everything that's bigger than 0 will be 1, everything smaller than 0 will be 0. Another popular one is ReLU. You can call that one using torch ReLU. And ReLU basically deletes everything, or puts to 0 everything that's smaller than 0 and makes the rest a nice linear line. Okay. There are different types of ReLU, which will come back later in this class as well. Okay. Now, when do we use certain activation functions? Okay. If we use if we're working on a regression problem, we typically want our output to be between minus and plus infinity, okay? Because we want to predict an actual number. So then we need to make sure that we use a linear activation function or something like ReLU, which allows for a wide range of outputs. When we're training our network, just like in logistic regression, we need a loss function. The loss function is the thing that we'll try to minimize when we're training our model. Actually, what does training a model mean with neural networks? We want to find the optimal weights. Okay? So the weights is what we need to adapt. Our loss will guide us in that process. Now, if we're doing regression, we can use a simple mean squared error loss, for instance. The mean square error loss, I'm sure you remember from last class, it just basically takes sort of the distance, the mean squared distance between the predicted output of the final node in the network and the actual labels. Other problems include binary classification. We talked about this at length last class. For binary classification, sigmoid is a very popular activation function which gives us basically confidence or probability. It outputs a value between 0 and 1. When we're optimizing a neural network for binary classification, we can use binary cross-entropy loss, again, which we derived during last class. Now we have multiple categories, not just binary categories. We can use something called softmax. I mentioned the softmax equation as well during last class, and basically we'll output 0 to 1 for each of the classes, and the total sum of all probabilities would be 1. Okay. So how does this look like? Imagine for softmax we have 3 possible classes, class A, B, and C, and we might, our softmax layer might output 0.1 for class A, 0.3 for B, and that means, by definition, that C needs to be 0.6. In this case as well, that means you're predicting that your input is part of class C. To optimize a categorical neural network, a neural network that does multi-class classification, basically, we use something called cross-entropy loss. When we're doing something called multi-label classification, that means we can have more than one output label for each example. In this case, we use softmax for each class, still with the total sum to be 1, but for our loss function, we can use binary cross-entropy loss for every class. Okay, so activation functions are very important because they are the ones that will allow us to learn very complex class separation borders, very polynomial. They introduce the nonlinearities into the network. So again, going from linear separation to polynomial separation. Okay, now let's take an example of a perceptron. What if we have a perceptron with the following weights? We have the bias weight 0 is 1, and we have W being 3 and minus 1. Okay, it's marked both in the equation here as well as here. Okay, so the weights are often put on the arrows. Now we can feed this into our linear regression model. If we fill this in here, then we can calculate the equation of the linear regression, which basically just is a line which we can show in a 2D graph. We can do it in a 2D graph because we have 2 input variables here. So it quickly outgrows 2D in real life. Remember, we still will be applying G, the activation function, later on. Okay. So in this example, we can draw the calculated linear line in this plot. Okay, simply by equating the output of the line, by equating this part to be 0. So assume we have a new input that we feed the network and we want to know the prediction. If we have an input x that is minus 1 and 2, that means that we can fill this in the equation, we just plug it in, and we calculate that it is minus 6. Okay, so here is again the point if we add it to our 2D graph. Now, if we apply the sigmoid function to it, we actually get 0.002, so we get our probability. So let's look at this graph in more detail. We have our linear separation line, and we have z, which is basically our linear regression. Z bigger than 0 or smaller than 0 defines our class boundaries here, and it is mapped to y using the activation function g. So in this case, the activation function would transform 0 to 0.5. So if you fill in 0 in the sigmoid function, you get 0.5. So if we build a neural network with perceptrons, how does that look? Now, we looked at this equation already. So we have the linear combination plus the bias of all the inputs plus the bias. And we can combine multiple of these perceptrons together. Okay. If you combine multiple ones into what we call a layer, you can write this in PyTorch as torch NN, neural network, linear. Okay. And a layer like this is typically defined by the number of input features, in this case 3, or M, sorry, the number of output features, 2, and the bias, if there's a bias. Bias is here, so we have it as true. All right, so that means that instead of just calculating this equation once, we need to do it for every node in our layer. So typically we have many of these nodes in our neural network. That means for each hidden layer node, we can write it as going from 1 to m, the number of inputs here. Summarize overall the inputs, the linear combination. And for the final output layer, for each of these nodes, we take the sum of these z's we just calculated here. And we summarize these over the number of hidden nodes. Okay. Now, when we design an architecture, as we call it, it's sort of an art. Okay. We need to design our loss. We need to design the algorithms we use to optimize the loss. How do we represent our data? Do we augment the data? How many layers do we use? How many nodes are there in each layer? All these hyperparameters, they influence the performance of our network very strongly. So whenever, for instance, you're doing a research paper on neural networks, it's important to not just say, this is our architecture. In fact, you want to test the architecture, maybe try a few different combinations, an exhaustive search of all these combinations, and report results for different configurations. Okay. All right. Now let's take a detailed look at this example. If we have, if we're calculating this for Z2, that means we take a linear combination of all the inputs, x1, x2, up until xm, which is represented here. We add the bias to it as well, which we can write as a simple linear combination, okay, from which, of course, the activation function will be taken. Now, we can expand this perceptron model to a deep neural network. What does that mean? Basically, we have many, many layers. Okay. The number of layers is the depth of the network. Okay, for each of the layers, there's an example calculation for a layer K. For each of these layers, you use the same formula to calculate the sum of all the previous inputs, after being fed through the activation layer, summarized over the number of nodes and k. Okay. In PyTorch, how does this work? It's pretty easy to define a neural network in PyTorch. For instance, here we have a 4-layered network. I'll go over the code first. First of all, we have some import definitions, as we always do. Whenever we have a neural network, we first define it as a class. Here I call it net, but you can of course name it as you want. Net is an instance of neural network module, so that's important. It always starts with an init function in which you define what type of layers you're going to be using. In this case, I'm going to be defining 3 fully connected layers. Fully connected layers are the types of layers we just saw. That means each node is connected to all of the nodes of the previous layer, fully connected. And each fully connected layer is what we call in PyTorch a linear layer. It has a certain input and an output. Okay. Notice that the output of the previous layer needs to match the input of the next layer. So if this were to be, I don't know, 20, this also needed to be 20. Okay. The final output here is 10. Now, by defining FC1, FC2, and FC3 doesn't mean I'm actually building the network yet. The building of the network happens in the forward layer. Okay, sorry, the forward function. So in the forward function, I call a first layer with ReLU activation. So the actual sequential definition of the layer needs to happen in the forward function. Now here I have an input X, which I get here. From X, I send it to the fully connected layer 1. Then I give it a ReLU activation. And I say, replace X with this. Then that same X is fed to fully connected layer 2 with ReLU activation again. And again, I call it X. And this continues, same thing through fully connected layer 3, except now I do softmax activation. Okay. So if you print net, then you actually will get a definition, just a few lines on what is being done in your neural network, so that can be a nice check for you. In the lab, we'll be looking at some of these things. Okay. So here's an example. Let's go through the calculation. Okay. Let's take a simple neural network with 2 features. Will I pass this class? It depends on the number of lectures you attend. It's not really the same. Let's say the number of video lectures you watch, and next to the number of hours spent on the final project. So we could represent all this in terms of these 2 variables. The green dots are the previous examples we've seen last year where people pass green or fail red. And now we have a new student that is a purple one here, and we're wondering, do they pass or not? Now that means if we feed our example data into the network, so we have a value for x1 and x2, we will get a prediction y hat, and we can compare this predicted value with the actual value. Okay. In this case, it doesn't seem very good because our predicted value is 0.1, whereby we want to predict 1 that it will pass. Okay. Now we can use the loss of our network to measure the cost from mispredictions. Okay. So L is a function that measures the loss based on the model weights and the actual values. Okay, so we call this function L, the loss, that takes as input the predicted values, compares them with the actual labels, and the predicted values are based on the current weights of the network. So that's good for one example. So we are looking at one student, 4 and 5. But typically, you measure your loss over an entire data set, more specifically the test data set, or sometimes a bridge data set, as we've seen. Now, in this case, our data set would consist of the previous student that we mentioned, but also a bunch of other students. Now, if we feed all these inputs through the network, we get a set of outputs, f, x. And for each of these outputs, we see, do they match? Yes or no? Okay. So basically, what we do when we calculate the total loss, J of W, so J given the weights of this network, we take the loss between the predicted and actual value and we average it over the data set. The data set here consists of n entries. Okay. So this J of W is known as the objective function, cost function, etc. Okay. Now, in the case that we use a binary cross-entropy loss, okay, something we discussed last week, we can actually calculate JW as follows. Okay. In PyTorch, it's very easy. You just say use BCE loss. Easier than doing the actual calculation, right? But if you take your slides from last week, you see that this corresponds to the formula of binary cross-entropy loss, where we take the actual values and we multiply them with the logarithm of the predicted values. We take 1 minus the actual value here, and we multiply it by the logarithm of 1 minus the predicted value here. Okay. So this again gives us binary cross-entropy loss, and cross-entropy, as you remember, is something, think of physics as well, surprise, something sort of the amount of chaos in your network. Okay. So we want to minimize J of W. Okay. If you're doing classification, that works. If we're doing regression, then we actually output continuous real numbers. So here our fx works a little bit different. In this case, we're predicting the actual grades and not if they'll pass or not. So in the previous slide, we had a probability of how likely it was that they passed. Here we have a continuous real number of the grades, meaning that our loss function JW actually also needs to change. We use mean squared error loss, for instance. There's other option. In PyTorch, again, very easily done. If you define the loss criterion, you just call MSE loss. And again, actually, if we would write this out full, the formula is a little bit shorter. You just take the difference between the actual and the predicted value, and you take sort of the Euclidean distance between them. Okay, and you average it again over the data set n, because there are n elements here. All right. So how do we train the models to optimize the loss functions? So we want to find the weights that achieve the lowest loss as we defined by our function JW earlier. So J, the loss of the network, the total loss of the network, given weights W. Okay. So when we do our loss optimization, we get into the domain of optimization, which is quite complex. But what we basically want to do is, suppose we visualize all possible values, combinations of weights, together with their resulting loss function. We could imagine an area or a landscape whereby the red spots would be the high value for the loss function. And what we want to do is we want to slowly move and find not a local optimum here, because we'd get stuck. We want to find the very best minimum, which is the global minimum. Now we can use functions like gradient descent to slowly make small changes in the weights until our loss function is minimized. Gradient descent is sort of the most basic algorithm. We'll see a few other options in a second, but let's start with gradient descent. Gradient descent, we start by initializing the weights randomly from a normal distribution. Then we loop the following until it converges to the best minimum. First, we compute the gradient. Remember that from last class? Gradient descent. So first we start by initializing the weights of our network randomly. There's some other strategies for initializing the weights, but gradient descent, we start from random. Then we loop the following until convergence to the global optimum. First, we compute the gradients, or the partial derivatives of the function jw given a change in weight w. And then we update the weights using the following formula. Okay. We calculate the gradient here. We multiply it by the learning rate mu here. And we subtract this whole term from the current weight to get the new weight. Okay. In PyTorch, it's done pretty easily. We just select the optimizer as being gradient descent. Then you feed it the model parameters, or the w's, which is what it needs to optimize, and you give it the learning rate LR. Okay. So during the model training itself, what you do is you loop over all the items in the data set, whereby you have x's and y's, and you start by by zeroing the gradients. So remove the gradients, put them all to 0. Then you do a feed-forward pass through the model. That means you feed the model your input and you get the predicted outputs. Okay. Then in the loss function, whichever loss you defined, I left it open here, you feed the target labels the predicted outputs y hat and the target labels y. Okay. Then we do a backward pass to calculate the gradients, and then we actually change the weights. Okay. This is gradient descent. So how do we compute these gradients? So gradients are an interesting feature of PyTorch. It's one of the reasons that all of these tools are so fast, because we are able to use something like gradient descent instead of calculating the full change of the final output function given a change in weights. We only need to calculate the change in weight, which basically is the strength of neural networks. So how does it work? In the case here that there's a change in weight 2 in our network, okay, here, we need to calculate the effect of jw given that change of w2. Okay. We can split that up in a multiplication of 2 terms. First, it would be the change in wy given a change in the predicted y. Okay. Then we multiply that with what is the partial, so the predicted change in y hat given a change in w1. Okay. So this is if we're calculating the predicted change in jw given a change in w1. So this is something called the chain rule. It means we can sort of split gradients or partial derivatives into a multiplication of their individual parts. Okay, so then if we're still calculating the change in jw given a change in w1. So we first, as we said before, we calculate the change in jw given a change in y hat. Then we multiply that by a change in y hat given a change in z1. So again we use this chain rule. And then we calculate a change in z1 given a change in weight 1. So you get the idea here. You're calculating the gradient of each step of the calculation that happens between between w1. It's fed first into linear equations to calculate z1, activation function, another linear equation, etc., etc. So using the chain rule, we just break it down into each individual operation. Okay. Let's look at a very detailed example here. Okay. So imagine you have a single training set. It's been given inputs 0.05 and 0.10, and we want the neural network to output 0.01 and 0.99. Okay. So the inputs here and the outputs here, the desired outputs. So how do we get started on this? So first we do a forward pass through the network. We just calculate what the predicted outputs are before we make any changes to the network. So for the hidden layer node H1, okay, we can start by taking the linear combination of W1 times the input I1, okay, here. Then we see that it gets an input from I2 as well, with weight W2. So we take the linear combination of this plus the bias, because there's also a bias in this network, which goes to H1. Okay. If we calculate all this, we get 0.377, which would be the value at H1. 5, sorry. And then in H1 there's an activation function. In this case there's a sigmoid activation, so we plug this in here to get the actual output of H1 after activation, 0.59. So then we do the exact same thing for H2. And you can calculate to see if you get the same results. Now we're going to repeat this for all of the output layers using the hidden layer as input. So we start with output, the output layer node O1. And this is basically a linear combination of W5, W6, and the bias B2. Okay, so again, all of this is plugged into the linear regression here. Let's say linear combination of input from all the previous hidden layers. If we calculate this based on our inputs, these are the H1 and H2 that we calculated in the previous slide, then we get the output 1.1 for the output layer. Again, we have a sigmoid activation. Plug that result in here, and we get the actual output after activation to be 0.75. Okay. Same can be done for O2. All right, so that's the forward pass. That's the easy part. In this case, we're using a mean squared error, so we can calculate the total error. Now remember, on the first slide of this example, we saw that the actual desired or the target label for O1 is 0.01 and 0.99 for O2. So mean squared error means you do the predicted value minus the actual value, and you square it and you take the average. Okay, so if we do that, plug in the target variable minus the predicted one that we got from the previous slide, we get 0.27 to be the loss resulting from O1. We also have a loss resulting from O2, so we can do the exact same thing from output node 2. Okay, now note that maybe it might be more intuitive for you to look at the total loss as sum of 1 until 2 of these error terms. It would mean like y minus y hat square. But we sort of already put the 1/2 inside the term. So this would be what we're calculating at each part here and here. Then we just need to add them up. So the 1/2 and the sum was already included here. Okay, just to make that clear. All right, the next step. We're doing our backward pass now. So first we did the forward pass, then we calculated the mean squared error. Now we're going towards the backward pass. And our goal will be here so we can calculate the gradient so we can change the weights. Okay. First, let's see how much should we change weight W5. W5, where is it? It is here, the weight of the last layer. How much will a change in W5 affect the total error? So that means we're going to be calculating this partial. This partial, we can use the chain rule and split it into 3 elements. Okay. the change in the total error given the final output layer O1, the final output layer given a change of the network output of O1, and then a change in the network output O1 given W5, a change in W5. Okay. All right, so notice here there's a small difference between the network output here and the output. What happens here is a sigmoid activation. Okay. So WNet is the output of the linear combination, and the output is a sigmoid after the sigmoid activation. Okay. So now for each of the terms in the following equation. So how much does the total error change with respect to the output? Well, first of all here, let's look back and remember our error function, mean squared error. We're going to be using that to calculate the change of the error based on it with regards to a change in the output O1 here. Remember from our previous slide that using the chain rule, we can split up our change in total error into 3 terms. So first, we're going to be looking at the first term here. So if we take the derivative of this first line, and we get the second line. Okay. How do we get from A to B, you might ask? Here's a little math refresher. If we take the partial derivative for a function x minus y squared, partial derivative for y, for change in y, then we get 2y minus 2x. Okay. Now, this is not a math class, so we're not going to go into details why. If you're interested in getting partial derivatives, there's a great website, I think I linked it to in the homework, Wolfram Math, which you can input any function, I'll give you the partial derivatives. So let's have a look. Here we have x minus y to the power of 2 and we take the partial derivative for y. Okay, so then we get x minus y to no power and times 2. So that's almost the same as we see here, except we see y minus x instead of x minus y. So that is easily adjusted by adding the minus 1 here in the multiplication. All right, so this is the partial derivative for the total error towards O1. So if we fill in our values that we calculated before, so target O1, we want the label to be 0.01, and our predicted label is 0.75. So here we get the first partial derivative. Okay. So remember also that this term sort of totally nullifies when we take the partial derivative. If we take the partial, it becomes 0. Why is that? Because there's no mention of out O1. So meaning the partial derivative of a constant is 0. Okay. All right, so the next step in our equation, this one. Remember this one, we're moving on here now. The next step is the sigmoid activation. So now we need to take the partial derivative of the sigmoid derivation, and I added a little math refresher here again. Now, to get from the partial derivative to this is actually very complicated. So instead of giving you 3 slides of math, I can refer the interested parties to this website, which is a very nice article that explains all the steps of the derivation and the calculation. But suffice it to say that the partial derivative of the sigmoid function is out O1 times 1 minus out O1. All right. So we can fill this in, again, the calculated predicted value times 1 minus the predicted value, and we get our next derivative. So how much does the total net input of O1 change with respect to W5? So a change in weight 5. This brings us to our last term we need for the partial derivative calculation, for the gradient calculation. And first we need to realize that the network output is a linear combination of weights 5, weight 6, and a bias. So we're calculating O1 here, the network output. It has an incoming value for W5, W6, and the bias. Okay, so it's just a linear equation here. If we take the partial derivative for Y5, it's very easy here. First of all, these terms become 0 because they're just constants and they don't contain a variable Y5, W5, sorry, Dutch for W. And then here we have W5 times out H1. Taking the partial derivative of that just becomes W5 times out H1. W5, sorry, to the power of 1 minus 1 equals 1 times the constant here. Meaning this is just out H1, which we had calculated before. Okay. Now, to get the final partial derivative, remember here, we need to multiply these three elements to get the final value. All right, so here's the formula again. Multiplying these three elements that we calculated gives us the total partial of the total error given a change in W5. Okay. Now let's get to the gradient descent equation. Finally, we know that the new weights are going to be the old weights minus the learning rate. Learning rate is just a constant that we set. Usually it's like 0.001, 0.01, but that's a different story that we'll get to in a minute. Times the partial that we calculated here, right? And this gives us our new weight, H5. So W5 will be updated to new weight. That's it. That's one step of backpropagation for one weight. Now we do the same thing for each of the weights in the network. Noting actually that to calculate a change in weight W6, W7, we still use the original value of W5. So we don't change the weight yet until we do the backpropagation for the entire network. Okay. All right. So let's move on. We've done all the weights here and here, but now let's move back to before the hidden layer or the hidden layer, and we calculate the partial for a change in weight 1. Okay. Now weight in weight 1 is a change in the error given the output of the hidden layer times a change in the hidden layer given the network output here, and a change in the network output given finally a change in W1. So using chain rule again, we get all these individual elements, and as you'll see, this will actually be further split up. So it's a very similar process, but we have to take into account that now the changes of weights, that the chain is longer basically, right? So the output of each hidden layer neuron contributes to the output and thus also the error that we're calculating of multiple neurons. Okay. All right, so if we take a look at the total error given a change in W1, I think we're still calculating W1, it's not going to only influence our output node 1 like we had in our previous example. This change in weight 1 also propagates like this, and it'll influence our output node 2. Okay, so we need to calculate both of these, meaning that we need to look at both partial derivatives summarized, because the total error is the error resulting from node 1 and node 2 in the last layer. Okay. Let's start with that first term, and the first term focuses on output layer O1. It can again just be split like we did earlier. It is network output here, partial of this times the partial of the network output given a change in H1. So we calculate this using the values that we actually obtained earlier. So our change in network for output for O1 given a change in the output of hidden layer 1, node 1, would be equal to W5. Why is that? So our network output can be written in this equation. Again, it's just a linear combination of the weights, these weights. Oh, sorry, these weights only, excuse me. And if we take the partial derivative towards H01, again, this term drops, then this becomes 1, and this is a constant, so it stays, so that means it's W5. The value for W5 is 40 here, which I removed for you, occluded for you. So 0.5 is this partial derivative. Okay, are you still with me? I know it's a lot of math, but it's quite, hopefully you'll see that it's always the same repeating process. You go through each step of the forward function, and for each function you take the partial derivative, you fill in the values. Okay. So again, we can plug in everything to get the change in error giving the change in the output layer H1 here. Same procedure for the second output node. So then, therefore, the total error is the sum of these two error terms, 1 and 2, and it boils down to this. Okay. So now that we know how the error responds to a change in the hidden layer 1, then we can actually go one step further down the network. And the first thing that we encounter there is a sigmoid layer. Right? Because first you do linear regression, then you obtain the sigmoid activation function, but we're going backwards here. So we first encounter the sigmoid activation function, for which we know now it's a very complicated derivative procedure, but it ends in the output of hidden layer 1, node 1, times 1 minus out H2, H1. So we fill that in, we get again our derivative. Now, the next step back is first we had the sigmoid. Now we have again the linear combination of weight 1 and weight 3. They all arrive in H1 and the bias 1. So this equation forms the network output in H1. Okay. So let's take the partial derivative for a change in W1. That means this is a constant, so it drops to 0 if we take the partial derivative. This is W1, is the partial derivative of x is 1, meaning that this becomes 1, and this considered a constant in the multiplication, meaning I1 is all that's left if we take the partial derivative. We fill that in. Again, I totally remove, oh no, here it is. I1 is 0.05. Okay, so putting that all together, using our chain rule, we multiply all of the terms and we get the final partial for a change in the error given a change in W1. And that's it. Okay, we can use this again in the formula for, this is a term we just calculated, the formula for gradient descent times the learning rate. The learning rate here is 0.5. Very often you'll see it's like 0.01 or quite small. And we have the old weight minus this term that we just calculate forms the new weight. Okay, and we update the network weights all in a similar fashion. Okay, easy, right? All right, so finally we've updated all of the weights. When we feed forward the 0.01 and 0.1 outputs, originally the error in the network was 0.29, etc. We calculated this. After a first round of backpropagation, if you were to change all the weights to the new weights with the plus sign that we calculate, you'll find this error, which is slightly less, as you see. Okay. Now, it might not seem much, but when you repeat this process 10,000 times, the error would plummet to a very low number here. Okay. So at this point, when we feed forward 0.05 and 0.1, the two output neurons would generate this very close to the target and this also very close to the target. And that is exactly what we want to achieve when we optimize or train our network. So in this example, gradient descent works very well for us. Okay. So how do we optimize this optimization process? Okay. Now, first of all, it's difficult. The main factor here that we need to determine is the learning rate. Okay. How do we set it? At least try a few different values. If you're writing a research paper and you're optimizing your network, try a few different values because it can have a really big influence. Okay. What you can have with your learning rate is if it's too small, it would converge too quickly. For instance, here, very small steps. Oh, I'm stuck here. I can't get out of this optimum. If you have too big steps, it would be unstable. It might jump from here to there, to there, to there, and just have trouble, misses the optimum basically, right? It missed the optimum. So that would make a very diversion. It wouldn't go down slowly. It would go up and down. So if you see your loss function going up and down, try a smaller learning rate. Okay. So our goal is here to find a stable learning rate that converges smoothly and still avoids local optimums, so is big enough to avoid those local optimums. Okay. So first of all, we can try different learning rates, but maybe smarter is we can design an adaptive learning rate that adapts to the optimization landscape. In this case, the learning rate is not a fixed constant, but it can be made smaller or larger depending on how large a gradient is or how fast the learning is happening, maybe the size of particular weights, etc. Okay, so here's this drawing that I just made, illustrated a little bit better. So what happens if your learning rate is too big or if it's too small? Okay. So, if we use gradient descent, it works well as we've seen, but there is the matter of this, which it's okay to compute, but it can be very hard to compute over the entire data set because you need to compute it for all of your training set examples, okay, which can be many. Okay. So that means that you might run out of memory if you simply try to put all of those vectors in there. So there's some solution for this problem. Okay. Oh, it's just to summarize what I said. This is a slightly differently formulated version of the optimization function in which they use theta instead of w, but it boils down to the same. Gradient descent, as you see, it's easy to implement, easy to understand, right? It has some disadvantages, so you can be trapped at local minima if your function is not convex, or maybe if it's if your learning rate is not set correctly. Okay, and it requires this large memory because it calculates the gradient on the entire data set. So how do we overcome this? There are a few alternate optimization algorithms that we can use. Now I put the PyTorch code here. So we're actually quite lucky in PyTorch. The only thing we need to do is define our optimizer and all the work gets done for us. All right, so here's one possible solution. Let's initialize the weight randomly like we were doing before. Now we can loop until convergence. Instead of directly calculating the gradient on the dataset, first we pick a single point I. For the single point, compute the gradient. You see a small difference here. J has a little y here. Now, we update the weights based on this particular gradient. Okay. So this is very easy to compute, but it gets very noisy because it's stochastic, right? You're calculating this for one data point. So it's going to be different if you use a different data point. It's not going to be optimized for the same ways. So small variation, which is what in the end we call stochastic gradient descent. Pick a batch of data points. Now compute the same gradient for one data point, but do it for the whole batch, and then average it. Okay. It's still fast to compute, and it's a much better estimate of the true gradient than just taking a look at one data point. Okay. And then again, same thing, we update the weights. That's it. So this is stochastic gradient descent. So it's a variant of gradient descent whereby we use a batch instead of the whole data set. It tries to update the model's parameters much more frequently. So it doesn't go through the entire data set, but it splits the data sets up in batches. So it can actually converge in less time because it updates these parameters quicker. It requires less memory because we only need to store the batch in memory, not the entire data set. And may get to new minimas. Exciting. So some of the disadvantages is there can be a high variance in the model parameter. Okay. So it may shoot up again after achieving a global minimum. Why is that? Because what is the global minimum might be, if we take a particular batch, it might have a different minimum than the global minimum for the data set. Okay, so that's sort of a balance, that it might temporarily go out of the global minimum. So to get the same convergent as the gradient descent, we need to slowly reduce the value of the learning rate. So by using these mini batches, we get a more accurate estimation, smoother conversions, all good things, basically. We can even parallelize the computation. Here's another type of learning algorithm, so optimization algorithm basically, whereby the learning rate is changed dynamically. So mu, or the learning rate, for each parameter is changed at different time steps. It is great that it changes because it can adapt better to the data. It's able to train on sparse data. But it is very computationally expensive as it makes use of the second order derivative. So it's a little bit more math involved. Okay. We won't go into details of ADAGRAD, but suffice it to say that it's actually learned in a very used in a very famous research paper on the GLOV model, which is an NLP, natural language processing model, and also a famous research paper on recognizing cats from YouTube videos. So it does work. But there are some adaptations to this algorithm, which is, for instance, Eta delta. It's an extension of the original ADAGRAD, and basically it removes a problem that the original ADAGRAD algorithm had, which was one of decaying learning. Okay, so its main weakness was that there was an accumulation of the squared gradients in some denominator, which basically caused a decaying learning rate problem. So instead of accumulating all these previously squared gradients, Eta delta limits the window of accumulated past gradient to some fixed size, so it doesn't look back so far, and that actually greatly improves the algorithm. Okay, so now the learning rate does not decay, but it's still computationally very expensive. Atom optimizer, very popular optimizer, adaptive moment estimation. It works with momentums of the first and second order, and the idea is we don't want to roll so fast because we can jump over the minimum. Okay, again, this sort of idea that we could jump back and forward, I don't know, okay, and sort of ignore the actual minimum instead of sort of slowly going towards the minimum. So I'm not going to go into details about how the maths inside these optimizers work, but suffice it to say that the method is very fast and converges rapidly. It doesn't have the decaying gradient problem, but it is still computationally costly. So keep that in mind when you're selecting an optimizer for your problem. Okay. So I found a little graph that compares the different optimizers. What we see here is Adam is typically quite fast. Adagrad seems more slow. Stochastic gradient descent also quite fast. Now take a note that this is for this particular problem, okay, which I took from a Medium site. But it's sort of interesting whenever you would be exploring how well an architecture looks, is to have a look at how quickly the optimization happens and realize that this can be different for different optimizers. See how slow Adagrad is. Okay. All right, that was a lot of math. Let's take a very short break. So what are some of the practical issues that we need to deal with when we are training models? We talked about different types of errors, bias errors, variance errors in the last class. But I want to quickly bring to your attention again that models can be underfitted, so they don't fully learn what's in the data. And they can also be overfitted. When they're too complex, they have too many parameters, too many exponents, coefficients, etc. So meaning they don't work well for new data, or they don't generalize well. Too often used remedies. So in addition to some of those that we already mentioned in the previous class, I want to mention these two because specifically in neural networks are very important. One is you might want to, this is for overfitting. One is you might want to reduce the number of features. Now this is an important one. Very often our networks become very heavy on the number of weights that we need to learn. You might say, what? We only saw like 6 weights in the previous example. But if you're looking at some of these deep neural network models, we're talking about 2 million weights they need to update each time a training set is done. Okay, so reduce the number of features can help you overfit. Maybe you also want to try a different model. CNN models, convolutional neural network models, typically have way less weights to learn than normal fully connected models. Maybe you want to manually select which features to keep or do some feature selection in advance. Finally, we also have regularization. So in this case, we keep all the features, but we reduce the magnitude or the size of the feature vector I. How do we do that? Okay, let's have a look at that. So how do we do regularization in neural networks? Okay, so how do we improve generalization of our model for unseen data? There's a few techniques. Drop out, early stopping, stop the training before it overfits to the data, augment your data, add some prior knowledge to a model. Let's look at some of these in more detail. First of all, we can drop some nodes. Okay. What happens or how does that work? We simply put some random nodes in the network, put their weights to 0 so they don't count. So we make our network a little bit sparser. Very easy. In PyTorch, you add a dropout layer. This will drop half of the nodes to 0. Okay. Interesting, and it can actually really improve your overfitting. Stop training before the network overfits. So it's very important, if you remember, to not just look at your training loss, because that's the loss that's standard printed when you train your model. Have a look at your testing loss as well. All right, we can augment our data. If we have more examples that are more robust, we can actually teach the model to become more robust for unseen data as well. And it might sound difficult, how do you create new data? But here's a very simple example. If you have an image, you could rotate the image, you can sort of compress it, you can rotate it upside down, you can add some noise. And if you add all these things to your data set, you make it more robust, meaning that your network will learn how to deal with all of these types of examples. Okay. In a data loader, in PyTorch, it's very easy to add some possible transformations to image. Rotate, flip right to left, flip upside down, add some random noise. It's very easy to add this while you're sampling your data for training. Okay. We can also regularize. So if we regularize, what we do is we sort of do feature selection by assigning a penalty to insignificant input features. Okay. So in our loss function, we add this term, which looks at the coefficients or weights, the absolute value, and depending on your regularization constant, you can penalize more or less. Okay. Okay. So if your lambda here is 0, then we don't have any regularization and we might be overfitting. If L gets excessively large, then we penalize all weights. Your model becomes super simple with a lot of weights and coefficients dropped, and that means that it's most likely going to be underfitting. Okay. Second type of regularization, slow, it's just a very variation basically of the previous L1 loss. It's rich regularization. It forces the weights to be small, but it does not make them 0. So this causes non-sparse solutions. So by taking the power of the coefficients to the power of 2, okay, it forces them to be small. Again, we have a regularization term. Okay, so how do we implement this in PyTorch? Okay, so L2 regularization is actually included in some optimizers. For instance, in Atom Optimizer, you can just put your regularization constant here, or you could do this manually. You define your regularization constants. Here we use Stochastic Gradient Descent Optimizer. We reset our gradients, so we sort of reset the training. We do a forward pass to get the outputs based on the model given some inputs. We calculate cross-entropy loss. So to calculate loss, we need the predicted, y hat and the target y, the real labels. Then we retrieve all the parameters from the model, from layer 1 and from layer 2. And if we do L1 regularization, then we can call the norm function, multiply by lambda 1 for layer 1, and we can call the norm function for layer 2 in case of L2 norm, we need to put a 2 here and multiply that by lambda 2. Okay, so our final loss will then be our cross-entropy loss plus each regularization term that we want to add. We do backpropagation and update our weights. So another great regularization method is batch norm. Okay. Batch norm comes from a paper in 2015. It allows faster training, improves regularization, reduces dependence on initialization of the weights. So sometimes a random initialization of the weights is not the way to go. It improves accuracy. And how is this done? Basically by ensuring that for each batch, the items or the instances are standardized with mean 0 and standard deviation of 1. Okay, so then we shift and scale the training instances. And what's interesting here is that the network during training can actually optimize this gamma and beta coefficient. All right. So this one is trainable. Using batch norm gives us a lot of benefits. Okay. So let's have a look at other network topologies. There are many different types of networks. Click this link and you can scroll down a little bit more. So we have the original perceptron from which we started. We expanded this to feed-forward neural networks, deep neural networks. Now we're going to very briefly look into RNN LSTM autoencoder later on in the last week of classes. Let's see what else we have. Denoising autoencoder, variational autoencoder, convolutional networks, and I think some may be further down the page. But this is actually very cool. If you know a little bit about machine learning already, go to this network, this web page, and have a look at which networks you're familiar with or not. First of all, if we're doing sequence modeling, so for instance, given an image of a ball, where will it roll to? If we have stock market prediction, given all the previous stock market movements, where is it going to go now? Okay. We need to be able to model our sequences. And to do that, we're going to be using something called recurrent neural networks, but we're going to be looking at that in a little bit. Other examples of sequence input or sequence data are sentences. This morning I took my cat for a walk. So given a sentence, how can we represent text? And I'm going to be talking to you very briefly about word vectors, which is, or word embeddings, which is a very popular technique in NLP these days. Okay. There's some traditional ways of representing text, such as bag of words, BOW. In bag of words, we just have a column for each of the words in the dictionary, and we put a 1 when they occur or a 0 when they don't occur. So in this case, we're representing our first sentence, I went to the movies yesterday. Okay. If I have a sentence, I went swimming, then it would be I went swimming. Okay. Something that is immediately apparent here is that what there are 20,000 words or something in the English language to represent I went swimming, I need 20,000, almost 20,000 zeros and 3 ones. So it's a very, very sparse representation. This is going to become a problem when we're learning models. A related but slightly more improved representation of text is TF-IDF, term frequency inverse document frequency. So this one focuses on the fact that rare words carry more meaning. So for instance, words like and are going to be having a very low value and others are going to be higher. How do we calculate this term frequency IDF? First of all, we have the term frequency, which is the number of times the term appears in the document, divided by the total number of words in the document. Okay. Then we have inverse document frequency, is the logarithm of the number of documents divided by the number of documents that the term appears in. Okay. Then we just multiply these two terms. Okay. So as I mentioned, so we're not going to go into detail of this. In my data science class, we talk more about this. I'm sure in the NLP class and maybe even the deep learning class, this will be explained in detail. But suffice it to say for now that these are very sparse representations. Very long vectors to represent a sentence, many, many zeros that we really don't need. So it's much more computationally better to look at less sparse model or dense modules, such as co-occurrence models. One such model is SVD, single value decomposition. I'm not going to go into detail in that, but I will focus on vector embedding models. Okay. Two famous ones, GloVe and Word2Vec. We will focus on the latter. So word vectors are all based on something called the distributional semantics hypothesis. This means, or this is defined as, you shall know a word by the company it keeps. John Rupert Firth made this hypothesis in 1957. What does it mean? Words that occur in a similar context tend to have a similar meaning. I enjoyed eating pizza at the restaurant. Okay, so pizza is a word and all that surrounds it is the company it keeps. I enjoyed eating pizza at the restaurant. I enjoyed eating pineapple at the restaurant. Because both of these words appear at the exact same context, we can assume that they share a similar meaning. And it's sort of true, they're both foods that can be eaten in a restaurant. Okay. So based on that principle, we can do unsupervised learning of word representations. So for each word, our goal is to get a vector of coordinates in a multidimensional space that is not 20,000 of size 20,000. Okay. Typically, word vectors are going to be like 128 or 256 positions long. So much more dense and sparse. A cool thing about these word vectors is if we project them into 2 dimensions, something we can do using TSNE, and something that we don't really have the time to go into right now. TSNE is a technique that you can use to project 3 and higher dimensional graphs into 2 dimensions. We can see some very cool things about these representations. So each word has a coordinate and hence a position in space. We see that these learned or these trained models have properties. In a very famous word-to-vec model from Google, they saw that if they do a translation, so a shift in space, of the exact same size from man to woman as from king to, then we see that we end up at queen. Isn't that interesting? That means that that translation with that angle and size equals a translation from male to female. Okay, we see similar translations to conjugate verbs, for instance. So these learned vector embeddings are actually extremely useful for representing words in a meaningful way, because the closer the words are, the more similar they are, and also we can define relationship between different words. Okay. Now, I mentioned there are some traditional methods like bag of words. If we compare these to word embeddings, we see that typically word embeddings are a lot smaller. They can be trained using a big text data set. And the resulting vector looks something like this. So it's not a bunch of zeros and one, it's a dense vector. It is not sparse. Okay. All right. So how do we train this model, or how do we get to these word embeddings? Typically, if we look at word2vec, there's 2 different architectures that are often used. In the first architecture, continuous bag of words, we have our input words, this is our sentence, and we project it into a 1-layer neural network that predicts the output. This is our word pizza, and this is the context in which pizza occurs. So we're teaching the network to predict a word given its context. In the second architecture, skipgram, we do exactly the opposite. So we give the model pizza and we learn to predict the context. Okay. Both of these models boil down to pretty much the same thing. Okay. All right. So we predict surrounding words for every word. Our training objective here, for instance, would be I predict what is the chances of the word I appearing given that the context or surrounding word is pizza. What is the chances of enjoyed occurring given pizza? What are the chances of restaurant occurring given pizza? These are the sort of probabilities that you're learning. Okay. All right, so it is trained. Here we look at the skipgram architecture. We give it the input vector. This is a traditional bag of words whereby we have the one word. There's one hidden layer and we classify all of the output surrounding words, okay, the probability. Now what's interesting here is after we fit this model, after we train it, what we're interested in is this hidden layer. So it's actually a very quick and very simple model to learn. It's one layer. to train it, we use cross-entropy. However, it's quite hard to compute. Okay, so because this loss function is hard to calculate, we approximate it and we do negative sampling. So what does that mean? We take words that appear in the same context. Those would be our positive samples. And we take words that don't appear in the same context. For instance, cat and glass. Then we feed those newly learned representations by the model to a binary logistic regression model. And if this model can easily classify, that means most likely that their representations are very similar or dissimilar, which is exactly what we want from this word-to-vec model. So this is a way to very quickly approximate the training objective. Okay. So the resulting model, the resulting word-to-vec model, is fast and accurate to predict. You can optimize the loss function very well. It captures semantic content, so it captures the meaning. It will capture both that pineapple and pizza are food, okay, without requiring any labels that say that pineapple or pizza are food. It's very popular. There's lots of pre-trained models available. That means somebody who's already applied a data set, a training data set to it and optimized the weights. And you can use these weights for different problems. Okay. It is super fast to train and it's very easy to use in Python. So before we actually look at the Python implementation, how do we actually get these word embeddings? Because fine, we calculate or we get a neural network here. What we are interested in, it's not the output layer. What we are interested in is the hidden layer, which is the latent representation of these words. Now, if we go back to where we were, the hidden layer here, basically, this weight matrix becomes our word vector lookup table. We use the hidden layer, I repeat, not the output layer, and we use this latent representation. This is what we call a representation in the middle of a network, a latent representation, as our new word vectors. Okay. All right, so in Python, we can easily, the most easy way is to use something like GenSim. In GenSim is a library that will just allow you to load word-to-vec, load word-to-vec vectors that are pre-trained from a particular model. Okay. Usually you can load the model. For instance, Google has a bunch of pre-trained vectors for a Google News. And you can just load these in a vector and then retrieve the actual word embeddings, which equates to having a word vector for each word. There's other ways to do this, of course, even within PyTorch, as we'll see in the lab. I remember when I did the first research paper on using word-to-vec, it was like pages of code in TensorFlow just to train a simple word embedding model. So luckily, a lot has changed in this area. Okay. All right, so back to sequence modeling. So we were talking about audio, time series, text, all being sequences that need to be modeled. We have a special type of model for this, because if we were to just feed words one by one into a neural network, we would lose any information about the previous word. For instance, we want to predict this here. France is where I grew up, but I now live in Boston. I speak fluent. Okay. So if we look back, let's say 2 words, from that you can derive that you need to fill in a language here. English, German, Dutch. Okay. We actually need to look back quite far to the beginning of the sentence to derive that we might fill in English or French. Okay. Now, bag of words don't preserve order. Okay. Even word-to-vec embeddings don't preserve the order of the sentences. Okay. All right. If we're training this, we feed it the window. So we try to predict this word given the surrounding training windows. But if we're actually going to do word prediction, we are not in a normal fully connected neural network. We don't look back. Okay. So we need a special type of model that allows us to assign weights to how far we look back. And this is what we call recurrent neural networks. All right. Recurrent neural networks take variable length sequences, they try to learn long-term dependencies, and they maintain info about the order. Okay. What's interesting is that they share their weight parameters across the sequence. Okay. They're typically depicted like this. So instead of just having the neural network arrow here, we have this recurring connection, let's say, that gives the module a sort of memory. Okay, so it can remember the past sequences. Okay. All right, so here we have a one-to-one vanilla or a very simple neural network. Okay, where we have one input and we predict one output. Okay. A different type of network would be many-to-one, whereby we have many inputs and we want to predict one output. Interesting here, if we use Herremans, is that there is a connection here, this memory connection, that allows us to look back to the previous word in a sentence, for instance. This is very useful. For instance, if you're doing sentiment classification, you have a whole sentence you want to input here, and you want to predict, is it positive or negative? Finally, we have an end-to-end model, many-to-many, whereby you have a sentence as input and you want to predict another sentence. Think of translations, music generation. You have one bar of music and you want to predict the next bar of music. Okay. There's many variant architectures here that are useful for different types of applications. So if we look at a recurrent cell, it's usually depicted by this sort of recurrent arrow, which will be expanded in the next slide. But it's noticeable that each cell has an HT, which is a hidden state at time t. This hidden state is updated at each time with a simple neural network operation, same as we are used to. We have a nonlinear activation hyperbolic tangent here, and we have a weight matrix multiplied by variables. In this case, there are two types of variables. We have our regular input variables, but we also have the previous time step hidden states. So in this case, that means that our weight matrix is split up in two parts as well. Finally, we calculate the output factor of the neural network by yet another neural network, weight matrix multiplied by the final hidden state, which we just calculated using this equation. Okay. Right, so as I mentioned, this recurrent neural network has a sort of recurring error. This is usually just done for clarity. If you write out the neural network in full, we'll see that we actually can unfold it through time. For each time, we have an input x0, x1, x2, etc. We have weight matrices that we multiply the x inputs with at each time. Note that all these weight matrices are the same over time. This is very important. Then we have a weight matrix that we use to multiply the hidden states with. So in the previous equation, these are this and this matrix. And then finally, we have a third weight matrix to get the final output of the cell. Note that these are the same. These weight matrices are the same, and these are also the same. This is important. Okay. Okay, so finally, from the output predictions for each time step, we can calculate a loss function at each time step, and the sum of all loss functions forms the total loss L. In PyTorch, whenever we want to include a recurrent neural network layer, we can just use this RNN command when we're defining our network. Interesting here is that we also need to specify the hidden size. So when we calculate the predictions, we do a forward pass. So the black lines here, these arrows that go forward, starting from X all the way to L. This is to calculate the predicted output. As you know, when we're training a neural network, we don't just do a forward pass. After that, we do a backward pass to get the gradients and adjust the weight. That is the red arrows in this drawing. But in RNN, the forward pass also includes going through time, right? So the errors are backpropagated at each individual time steps and finally across all time steps. That means that backpropagation through time is being executed, which is a special technique, and it is quite hard to do. One problem that we see at RNNs is the problem of vanishing gradients. Okay, so we see again here the forward propagation of the hidden weights, the black line, and then the back propagation the other way around. Okay, now computing these gradients, sorry, with regards to the hidden, the hidden state 0, the first time step involves many factors of this weight matrix. Remember, it's always the same, plus repeated gradient computation. Okay. This can be problematic for two reasons. Okay, first, if any of these values involved in the repeated calculation, such as either the weights or the gradient themselves, become bigger than 1, then we can have the problem of exploding gradients. Okay. In this case, we can perform gradient clipping to just scale down the big gradients. A more important problem is if these values, either the weights or the gradients, are smaller than 1. Then we get a vanishing gradient problem. So you can sort of imagine if a value is small, you multiply it by another small value, and yet again, and maybe over a few time steps. In the end, you'll get something that is immensely small. Okay, and this can happen very quickly. Okay, so it can sort of be an explosive reaction. So there's 3 ways in which we can adapt this, and we'll just go over all 3. First would be through the use of special activation functions. Secondly, by initializing the weights of the network differently. And thirdly, by making some changes to the network architecture, more specifically the type of RNN cells. Okay. So why are these vanishing gradients a problem? As I said before, if we multiply a lot of small numbers together, we actually propagate this error back in the past. It's harder to propagate these errors back in the past because we'll end up blasting our network, so biasing our network to capture more short-term dependence. Okay, so basically the network is forgetting the longer-term errors. Okay. This can be a problem. If you remember the sentence, I grew up in France, I lived in some other place sometime, and I speak fluent X. If we're predicting the X here, we need to look back really far to France. And if we have a vanishing gradient problem, then we will not remember the old states very well. Okay. Right. So it biases your network to learn more short-term dependencies instead of long-term dependencies. So the first trick we can apply is to use a different type of activation function. Okay. If we use a hyperbolic tangent or sigmoid activation, the derivative is actually smaller than 1. Okay. But if we were to use ReLU, if you remember, if x is greater than 1, it just becomes 1. The derivative is 1 whenever x is bigger than 0. Okay, so this would help prevent our shrinking gradients. Okay, but only when x is bigger than 0, mind you. It's quite important. Second trick, initialize the parameters of the network. Usually we do random initialization, but there's actually better ways to optimize if you're dealing with vanishing gradients. Okay. Apparently, if you initialize to an identity matrix, remember what that is, like the picture here, we have 1s on the main diagonal and 0s otherwise. This will help the weights prevent from shrinking to 0. Thirdly, there is a different type of RNN cells, those that have gates. So they're a little bit more complex, but they help control which information is passed through. So for instance, long short-term memory networks, you have also gated recurrent units, GRU. They're very popular types of RNN cells because they're able to use gates to control, forget, update information through many time steps. Right, so if we have an RNN cell, simple computation mode, as you know, we have our input xt, we have our output xt, and we always pass along the previous hidden state, apply the hyperbolic tangents, neural network computation, and get the next hidden state. So if we look at a variation of this single RNN cell, we can look at LSTM cells. LSTM. So these are computational blocks that control the information flow. I'm not going to be going into details on the mathematics of the LSTM cell, but I want you to understand the concept, okay, of how they have an ability to track information over many time steps. If you're using PyTorch, the only thing that changes is here you define LSTM instead of RNN when you make your model definition. All right, so LSTMs have 4 kinds of gates. So they do 4 types of actions. They forget information, they store information, they update, and they output the results. Okay. So first it decides which information to remove from its state, okay, through the forget gate. So all of these gates, they're represented as a sigma sign. This is because they're basically sigmoid activation functions based on a linear combination of weights again. So a simple neural network operation with sigmoid activation. So in a forget gate, you take as input the xt, so the inputs, and your previous hidden state. It calculates how much of the information is going to be forgotten or retained, 0 or 1. Or any number between 0 or 1. Then we have the store gate. Store gate takes the same inputs, the xt's and the hidden states of the previous time. And this is a little bit more complicated. It has, like previously, the hyperbolic tangent to sort of our memory, to calculate our memory. Again, pointwise multiplication with an activation function. And it also has a sigmoid function here, which basically will tell the this hidden cell state what to remember. That brings us to the cell state. So as you noticed, there's not only hidden state that flows to the cell, but we have a cell state. The cell state forgets whatever is the forget gate tells it here. Remember how we calculate this in the forget gate? It adds whatever the store gate tells it, and hence it predicts the new cell state. Okay. So basically using this formula, just adds the two. All right. Finally, we have the output gate. The output gate, again, takes in the previously hidden state and the XTs, does a sigmoid activation, and calculates the hyperbolic tangent of the pointwise multiplication. So this output gate controls what information will be the next hidden state and will be sent to the next cell. Okay. Right, so one of the advantages of the LSTM cell is that the internal cell state, so the C, causes an uninterrupted gradient flow, which means that typically LSTMs won't have a vanishing gradient problem so much. That's amazing, okay? Because the information can just flow back straight through the cell state. Okay. Right, so there's some other types of RNN cells, GRUs, so they have a sort of peephole connection, so they can always look back at other cell states. Another very popular algorithm these days, and it's not an RNN algorithm, is an attention mechanism, attention network transformer networks. You might have heard of models like BERT, very effective models that they look a little bit like an LSTM in functioning, but they're programmed quite differently. They're very good at doing translation tasks. So for instance, in the picture below, we have an English sentence translated into French. Each word of this sentence, at each time, suppose we're predicting zone. In this case, the attention network will look at which surrounding word to focus on. Okay, so it will learn the weight of these connections. Okay, so this is something that we sort of automatically do when we're listening. Some words stand out more. And this is exactly what the network is trying to learn. It's quite effective and it works on a multitude of problems as well, but it's very recent, like only the last 2 years. So in this week's lab, we'll be putting everything together in PyTorch. We'll make a simple neural network. For those of you daring, we'll do an RNN for a task of sentiment prediction. That means sort of a combination because we will have a word, a sentence actually of multiple words, which need to be put into their word-to-vec notation, which will then each be fed into an LSTM network to output one sentiment value. Okay. We'll check out how to program batches, regularization, dropout, batch norm, all these things that we discussed in this week's lab. All right, so remember, if you have any questions, please visit the forum and ask me any silly question about the class, about teaching. We can discuss anything there. And I'll see you on the Zoom session on Friday.